All the information is in the Discord channel, so you can go there to have a look what is necessary for playing with the images and the data that we are going to do here. So we assume that you have already installed Gnuastro, for example, using Conda with the instruction that we gave there. But just in case you didn't do that, you can download the Gnuastro and all of the dependencies with Conda. And then now we assume that you have already done this, and now let's go to the action. So here I have a directory in which I have already downloaded all of the images that we are going to use. During the vast majority of the tutorial, we are going to use just one single image. This one, for example, it doesn't matter which one of them, but just one single image. And then at the end, we will start with the more complicated things in which I will show how to use, for example, different images for obtaining color images. Okay, so let's start step by step. Once you have installed Gnuastro, you can use all of the programs that correspond to the Gnuastro collection of programs with this way. So you just have to type in the command line AST, and then you will see all of the programs that belong to Gnuastro. All of them start with the letter AST. So you have here different programs with different purposes. The only one that is not part of Gnuastro is this one, is astrometry engine that corresponds to the astrometry.net software for obtaining the astrometry of the images. But the good news is that right now we are working really hard in order to include all of the necessary libraries and programs in order to make the astrometric, to obtain the astrometric solution of the raw images, of astronomical raw images, just using Gnuastro from scratch. So we hope to have everything ready in a couple of months, and now we will start reviewing the programs of Gnuastro. So the first one that we are going to use is AST fits. This is one program that we use a lot because its main purpose is to check the metadata of the images, the headers, and manipulate that metadata. So the way you have to use this program is just to type in the name of the program on the command line, and now the name of the image that you want to check. So for example, the image this image in this filter, and the first thing that you will see is that it prints on the command line the name of the program, the version of Gnuastro. In this case, we are using the latest one, so 0.16, and then it gives to you all of the information related with this file. Okay, so in this case, it says to you that you have 4 different extensions. The first one is just information. It contains no data, and then the next one correspond to images. So they are of a type of float 32 images with this dimension. Okay. So now, if you would like to have a look at the inside of, for example, the first extension, you just have to type here --HDU equal to 1, and then you will obtain the header of this first extension. Okay, so this is really simple. Then the way you have to specify this, you can let here one white space. It will give exactly the same, or with shorter options. So for example, H1 or H white space and 1. So they are the different ways we have to specify the arguments of the Gnuastro programs. So let's continue little by little. So one of the things that another very interesting thing is that is the option, for example, -- pixel scale. And as you can see here, this is gonna give to you some information related with the world coordinate system. Okay, so for example, the size of the pixel along the 2 different dimensions in degrees or in arc-second per pixel, which is more common in astronomy. And then also another option that another interesting option that you can use is the sky coverage. Okay, so if you type here sky coverage, this command line, then it gives to you all of the information about what is the region of the sky that is covering this, this image. Okay, so all of the different options that are available for each program of Gnuastro can be seen with the option --help. So by doing this, you will see all of the different options that you have that you can use with this particular program. Okay. Okay, let's continue. Let's go. Now we are going to manipulate some of the keywords that are inside of the extension number one. So for example, let's have a look at the extension number one again. And now we are going to pipe this into grep just to have a look at which lines start with the keywords PC. Okay, so you will see that here we have 4 different lines. And now consider, for example, that we would like to remove these 2 different keywords because the numbers that we have here are very small. Or for any reason, you just want to remove these 2 different lines. So the way you have to do that is just specifying here --delete, and then the keyword PC1, sorry, 1, 2, and --delete PC2, 1. Okay, and if you have a look again at the image, you will see that how they have been removed. So this is very powerful, and you can see that just directly from the command line, we can manipulate and also obtaining really useful metadata from our images. So now let's have a look at the image itself that we are going to use along the tutorial. To do that, we are going to use DS9, this program for visualizing the astronomical images. So this image again, just to have a good feeling of what we are going to use along this tutorial, okay? Just to see the object, the astronomical objects in this image, let me change the scale, okay? And here you can see that that this image corresponds to the Hubble ultra deep field, and in this particular case, these images were reduced by Alejandro Borlaf by the time he was a PhD student at the Instituto de Astrofísica de Canarias. And the main goal of this work was to reduce completely from scratch all of these images to preserve the low surface brightness structures around the galaxies. So he used many different programs from Gnuastro in order to model the sky appropriately and then preserve that kind of very low surface brightness structures. And as you can see here, if I do again AST fits -1, you can see that, but that time Alejandro Borlaf was using Gnuastro 0.7, and now we are using 0.16. So since then, we have improved a lot Gnuastro, all of the Gnuastro programs and libraries, and it is much more mature, and it can do very powerful things, as we are going to see. So let's continue with the next program I want to show here. It consists in the AST prop program, and the main goal for this program is to make cuts of images, so just to select a different region of one image. So for example, if we specify here again an input image, which is going to be exactly the same, then we can give some coordinates and some width in order to have a crop of the image. So since we are going to provide right ascension and declination coordinates, we have to specify here that the mode is in world coordinate system. And now we have to provide the center. And I will give this center, which is centered in one particular galaxy, comma, this is the right ascension, comma, the declination 27.7853. And now we specify the width, the size of the image. So width, we say we want 20 arc seconds, so we have to divide this by 3,600, which is how many arc seconds are in 1 degree, because here we are specifying the coordinates in degrees. And now we can give an output name. So dash dash output, and for example, crop. If we run this, you will see that just in less than 0.1 second, it has computed the crop from the original image. So now let's have a look. This is really fast, as you can see. And this is the result that I am obtaining. So a smaller image that I was able to construct just directly from the command line. Okay, as you can see here, we can have a look now with AST fits at this image just to, crop, just to check that again we have two different extensions. The first one just with the metadata, and then the size, so the dimension of the second extension and the data type. So now let's do more complicated things. So let's open again the same image just to show you how we can obtain a more complicated crop regions, because a square one was really easy to do. So here again, let's change the scale. So for example, imagine that I would like to crop a very strange shape of this image. So go to region, shape, and now we are going to change the shape to polygon. Okay, and now we are going to define here a very strange polygon on the image. For example, you make the shape of the polygon as you want. Okay, so for example, something really strange, which in principle makes no sense, but this is just to show an example. Okay, so now that you have defined this very strange polygon, you just have to go to region, save as a DS9 region. Okay, I also put here I always put here degrees. Okay, I save this, close, remember the shape, which is really strange. And now you just have to specify this very strange region with the option dash dash polygon, and then DS9 region, and let's put a good name. So for example, dash output polygon. Fits. What's happening here? I'm having here the AST fits, so AST cropped the original image. Sorry, I was specifying the already cropped one. So just very briefly, AST crop, the image that we want to crop, so the original image, then the option polygon with the regions, and then the output name. So if I execute this, you will see that in this case, polygon, we have the output image with that region that we have previously defined. Okay, so very strange, but this is just to show that we can make very complicated things with this program. And another very interesting feature is that it preserves by default the world coordinate system. So it doesn't matter on which region of the sky you make the crop, that it is going to compute the necessary new information about the astrometry of the image. Okay, that's good. Now let's continue with another program, which is NoiseChisel. So NoiseChisel was presented, the name is this one, so AST NoiseChisel, as you can see here. So it was presented in ADAS 2015 in Sydney, but that time this was at the very first moment in which Mohammad presented to the public, and since then it has evolved a lot, and now we are going to see how we can use this program for making the detection of the signal of our astronomical images. So again, let us specify here the input image that we are going to use. And now let's give a good output name. So for example, NoiseChisel.fits. And just let it run. As you can see here, it is using the 16 CPU cores that I have in my laptop. Now let's have a look at the output that it has computed. So DS9, in this case, I am gonna have a look at all of the different extensions. So I will type here multi-extension cube. and then the NoiseChisel output. NoiseChisel output, press enter, and now we will see the different extensions that NoiseChisel has computed. Okay, so the first one, let me change the scale once again. So the original one, sorry, the first extension is the same than the original one once NoiseChisel has subtracted a sky background model that it computes internally. Okay, so this is the very first extension that we have. The second one is the detections that it has computed. So this is a binary image in which all of the pixels that are white correspond to ones, and that means that here we have signal, and then the zeros, which correspond to the black pixels, they are sky background. So if I change in between the original image and the mask, the detection image, you will see that all of the different signal, all of the object has been detected as signal. And then the third extension is the sky background model that NoiseChisel computes by default. Maybe changing the color, you will see it better. And then the last extension is the sky standard deviation. Okay. So it automatically computes this from the original image without any assumption on the shape of the detected region and so on. So this is non-parametric. And now we can have a look at the files with AST fits once again. NoiseChisel.fit, and this is actually what we were having a look with DS9. The first extension is just the information that the parameters that NoiseChisel has had used for obtaining this detection image. Okay. Okay, now let's move to the next program, which is AST arithmetic, which is a program with the goal of making calculations, the manipulation of astronomical images. So the first thing that I want to note here is that it uses the reverse Polish notation. So that means that, for example, if you want to multiply 2 by 3, you cannot specify like this, the order of the operands like this, but you have to do 2, 3, and then the operator, which is the multiplication. Okay, and then it is gonna give to you the result. So 2 by 3, it is 6. So then we have many different operators. So for example, here we could take, for example, the square root of 6, and it will give to you this number. And then, for example, if you don't want to have this information, so this additional information, you just have to run in quiet mode. This is also common for all of the Gnuastro program, this option. And in this case, it's going to show you only the number that you are asking for. Okay, this is very simple, but once again, we can make very powerful things with this program. So for example, the sum of 2 different images. To keep the thing easy, just let's do it, AST arithmetic. Now let's specify one image. We have to specify also that we want to sum the extension number 1 of this image and then the other image. Download, for example, the other filter, the extension number 1, and now the operator that we want to use for making the operation. So we want to sum these 2 images, so to specify here plus. Okay, and now let's give an output name and just press enter, and it is going to compute the sum of the 2 different images that we are specifying here as an input. Just let's have a look very fast here to the sum image. Of course, this is just summing 2 different images, which is easy to do. But in the same command line, you can sum thousands or hundreds of images, and it will be done in parallel just with one single command line in the terminal. Okay, so this is the result. This is the sum of the 2 different images. And you can use many other operators. There is not only sum or median or something like this, but we have many of them. Just to have a look at some of them, you can go to the book into the website of Gnuastro to check all of the different options that we have, but you can also have a look without going out of the terminal. So just type here info arithmetic, which is the program that we are using, and then, for example, arithmetic operators. Operators. And here you will see a very nice explanation on all of the different things that you have to take into account, and then all of the different operators that we have. So, for example, we have trigonometric and hyperbolic operators, the statistical, units conversion, filtering operators, stacking operators, and so on. So you have many of them. So, for example, if you would like to stack many different images, you could stack all of them using the mean, the median value, sigma clipping, so rejecting outliers values, median, standard deviation, and so on. So this is really powerful, and you just have to type the command into the terminal. Now let's go and use arithmetic for making something more complicated. So, for example, we are going to use the detected image of NoiseChisel. So once again, let's have a look at this, of the different extensions that we have in this output. So you can see here we have the detected extension. And now the thing that we want to do is to mask all of the pixels in the original image that correspond to the signal in the detected image. Okay, so we can do this with AST arithmetic. So we have to specify the images that we are going to use. So NoiseChisel extension number 1, this is going to be the data that we want to mask, and then specify the second extension, which is the mask that we are going to use. Okay, and now the operation that we want to make. So since this is a binary image consisting in 1 and zeros, we can just say here we want not a number values where the second image is equal to 1. Okay, and then we just have to give an output name again. So let's call this only sky, for example. And here you are. Really fast, we have computed the mask of this image. Let's have a look. Only mask, and you will see what's happening. Here you are. The original image has been, so all of the pixels that were considered to have signal in the original image has been set to not a number values, as you can see here. And the rest, so you can see the values pixel here, and then the rest of the pixels remains as they were at the very beginning. Okay, so that can be done with arithmetic. We can do exactly the same, but the other way around. So putting here not, this is another operator. In this case, we are going to make the detection, the mask of the sky background, and only those pixels that were having signal will remain untouched. So, for example, only detections, and here you are. Just have a look. Only detections, and this is, let's say, the complementary operation to the first one. So here you can see that all of the pixels, let's change the scale again, that all of the pixels that correspond to the sky background that were computed by NoiseChisel, now they become not a number with the operation that we have just specified. And now here we have the remaining objects without not a number values. Okay, so you can make even more complicated things, as you will see later. But now let's move to another program, the next one, which is segment. So once NoiseChisel has computed the detection of the signal from our astronomical images, we can break that signal into different parts. So we are going to use here AST segment for making the segmentation of the signal. So let's use this using as an input the output of NoiseChisel. So NoiseChisel has detected the pixel that has a signal. So now we have to specify AST segment, NoiseChisel, and that's it. Let's give as an output a good name. So segment.fits, and let it run. So it is also really fast, and let me put fits just in case something happened. And now we can have a look again with the DS9 multi-extension cube, and then the segment image. And then you will see that now we have different extensions for the different clamps and objects that segment has computed. So let's change the scale. This is the original image, as you can see here. And now if I go to the next extension, you will see that now the signal has been segmented into different clamps. Okay, so this is one object, as you can see here. And then it has been broken into different clamps, different group of pixels that correspond to one structures. So if I change in between the original and the clamps extension, you will see that all of the structures correspond to the clamps extension. And now we also have another extension which corresponds to the object. So let me change the color bar. As you can see here, each different group of clamps belong to one given object. So this is one particular object, and within this object we have different clamps, as you can see here. Okay. So now let's do the next experiment. Imagine, for example, that you would like to study the outer part of this galaxy. Okay, so once you are able to detect the object far away, okay, using NoiseChisel, and now that you have break this into different objects from this one to this one, and then also you are able to segment the different parts of the same object into different clamps. Okay, imagine that you would like to study the outer part of the galaxy, the low surface brightness part of this galaxy. So you could make a combination of this mask, the clamps mask, and the object mask. And for that particular experiment, remember this value. So the value that you can see here for this object, 1206. And now let's use arithmetic for make more complicated things. So we are going to mask all of the objects and all of the clamps corresponding to this object to only study the outer part of this galaxy. So let's just do it step by step. Remember that just in case you have any problem or any doubt, Mohammad Akhlaghi is in the Discord channel, so he can solve any kind of problem you may have. So let's use again as the arithmetic. Okay, and now let's use a very nice feature of arithmetic. So let's specify, let me remove this one. Okay, arithmetic segment. Let me, before that, show the different extension, just to have it in mind. So here we have the different extension that we have. And now let's go with arithmetic. So AST arithmetic, the segmentation, extension number 1. This is the input image. And we are going to call this dataset as data. So this is a feature here that we can use, which is set-data. Okay, so now inside arithmetic, data is the extension number 1 data. Okay, so let's do exactly the same, but for the extension number 2, which are the clamps. Let's call this clamps. Okay, and do exactly the same with the extension number 3, which is which correspond to the objects. So set objects. Okay, And now let's do the operation. We want to multiply the extension number 1, which is, sorry, the extension number 2, which are the clamps, by the extension number 3, which are the objects. So you just have to type here clamps, objects, and then X. Remember the reverse Polish notation? You have to put before the operands and then at the end the operators. Now we want to call this, for example, combine. Okay, so set dash combine. Okay, so this is there in combine. We are keeping the result of multiplying these two extensions. And now let's mask on the original image those pixels that are not equal to a given value, which correspond to the value of the object that I said before. So data, we are going to use the combine mask. Okay, and now we say minus 1206, which is the value that we don't want to mask. So we say not equal, and then put none values where this condition is true. Okay, and then we just have to give a good output name. So for example, mask dot fits, and then execute that line. And you will see that really fast. So this is almost 0.02 seconds. It has computed all of this operation and it has given to you the output image. So let's have a look using DS9, so mask, and you will see what is the result of this operation. So as you can see here, we have used the different mask, the clamps, and the object in order to only have the very low surface brightness features around this kind of clamps for these particular objects. And all of these have been done in one single line into the command line. So you can this is just to let you know that you can make many powerful things just using these sets of programs from Gnuastro. So now that we know how to use arithmetic and that we can do many things, let's move to another program, which is AST make catalog. AST make catalog. This program was presented in ADAS 2016 in Trieste by Mohammad Akhlaghi. And now I am going to explain how to use this program, for obtaining astronomical catalogs, astronomical tables from our images. So once we have constructed, once we have detected the signal and we have break the signal into different objects, we are able to make measurements over that images. So for AST make catalog, you just have to specify the segmentation image that came from the program AST segment, and now just specify the different measurements that you want to obtain for your catalog. So for example, let's specify here the labels, the IDs of the objects, the right ascension, the declination, so the coordinates. Let's put also the magnitude, the signal to noise, the axis ratio. Okay, and then in order to be able to have a good magnitude values, we have to specify a 0 point. So for example, 0 point equal to, for this particular image, it is 2594. And then let's also ask for a clamps cut, not only for an object catalog, but also for a clamps cut. Okay, and now let's give a good output name. So for example, catalog.fits. And that's it. Really fast. Again, it has computed the catalog. And now we can have a look with AST fits at the catalog that we are obtaining. And as you can see here, inside of this file, the catalog that we have previously obtained, we have two different catalogs, one for the objects and the other one for clamps. Okay. Now, for example, if you would like to obtain the catalogs in plain text format, you just have to specify here the extension txt. And in that case, it will compute two different catalogs, so two different files, one for objects, as you can see here, and the other one for plants. Now we can have a look at the catalogs itself. So catalog, for example, for the objects, and you will see that here we have different columns that are the ones that we have requested. So let's remove the txt files because we are going to work with the fits files. So now that we have constructed one catalog, we are able to go to the next program, which is AST table. And this program is aiming to manipulating astronomical tables. Sorry. So here you just have to type AST table catalog, and then it will print on the command line the catalog, the measurements, so actually the data of the catalog. So if you want to obtain, for example, only some data of this catalog, the metadata, you just have to specify here --info or -i in the short option, and it is gonna print on the command line how many different objects do you have in your catalog and the different columns measurements that you obtain with this particular catalog. Now imagine that you have a very huge, very large catalog and you only want to use some of the columns. So you can do that with the option column equal to, for example, right Ascension. You can specify, of course, another one, column equal deck, to obtain the right ascension and declination. And actually, you can do this much shorter, just putting a command in between the different names of the columns that you want to obtain, and even shorter with the option -c and the name of the columns. Okay. Of course, you can also use the number of the columns, so the position of the columns is then instead of the name. So column number 1, number 2, and number 3, and it is gonna print on the command line the columns that you have specified. Okay, and now imagine, for example, that you want to keep these columns as another table, just because the original one was very large. So you just have to specify here the output name and say, for example, sub catalog.fits. Okay, and it is gonna save all of this into a new catalog. So AST table sub catalog, just to have a look, and you will see that now this is the result of the previous operation. If you want to, for example, have a look at some objects that are within a given range of magnitude. So for example, let's print everything here. And now imagine, for example, that you only want to have in your sample only the objects that are within a given range of magnitude. So you can do that by specifying here with the option range. So range equal to the column name, so magnitude, and then comma the first value, so for example 26.99, and then the other value, the other extreme of the range, so 27.0, and it is gonna print on the command line only those objects for the condition that this is true, that are in this range of magnitudes. Again, you can do exactly the same, but adding another condition. So for example, I want all of the objects that are in a range of axis ratio in between, for example, 0.6 and 1. And then it is going to print on the command line only those objects that are true for these two different conditions. And now imagine, for example, that you would like to sort this sample by the signal to noise ratio column. So you just have to use the option --sort and then the column name. So signal to noise. and it is going to print in order. So this is the very first one, so the smaller signal to noise ratio value, and this is the largest one that of course falls within these two different range of magnitude and axis ratio. If, for example, you would like to count the number of objects that you have in this sample, you just have to type this to the program WC and count the number of lines. So in total, we have 8 different objects within our catalog that with this range of with this criteria. And now moving into another feature, which is the arithmetic column with AST table. So once we are able to sort, to manipulate, to filter our data, imagine, for example, that we would like to obtain the magnitude column, but in millimagnitude. So we want to transform the magnitude column to millimagnitude, okay? So we can do this directly with AST table. So let's put, for example, the column here, magnitude. Okay, this is gonna print the original magnitude column. And now we want to operate this column. So we just have to type here C, and then quotes, sorry, in small single quotes. And now we are going to specify here arith, because we want to make some operations, and then the column that we want to operate, magnitude, and then we want to multiply this magnitude column by 0.001, and then the operator. And it is gonna give to you, the result. So once we have multiplied the original column by 0.001. Of course, this is very simple. We have, again, many different operators. So let's make another one more complicated. So imagine, for example, that here we want to transform the right ascension and the declination of this catalog into pixels position of one particular image. Okay, so we can just specify here this operation. We want to make the following operation: right ascension, declination, and now we are going to transform the WCS to image coordinate. Okay. If you just press enter here, it is gonna, sorry, I'm missing here EMG, and it is gonna complain about not having astrometric information. And this is because you are trying to transform the right ascension and declination, but of course, AST table with this operator needs some WCS information, for which we are going to give, with this option, WCS file, the original image. So for example, download and this filter. Okay, so now it is gonna use the astrometric information within this image to transform the position on the sky to pixels position. So press enter, and you can see. So for this particular image, the position on the sky that correspond to these coordinates are the pixel in these two different columns. Okay, we have many different operators that you can have a look at the Gnuastro book, but this is just one single example in which you can see the different things that we are able to do. So let's move now to another interesting program, which is AST Query. And as you can imagine, this is for making queries to astronomical databases, for example, Gaia or BCR. So if you type here AST query Gaia --info, you will see that here we are retrieving all of the data, all of the metadata that belongs to the Gaia databases. So we have here 134 different tables that we can use directly from into the command line. So for example, just to specify a given dataset here, we can say we want to obtain the data release number 3 of Gaia. So let's print the information, and you will see that for that particular dataset, we have the columns names, so you can obtain that information from here. Okay, another interesting feature is, for example, to have a look at another data set. databases, for example, this year. And now imagine, for example, that you want to look for some particular keywords. So just to specify here, limit info. And I'm going to type here my two surnames. So Infante-Sainz, okay, and just let's go and look for this keyword into the BCR databases. As you can see here, I have a couple of data sets that I sent to BCR. Actually, this is the one that correspond to the images that we are using for the tutorial that were published by Alejandro Borlaf in a couple of years ago. The next one is about the low surface brightness of some galaxies, and this one corresponds to the Slow and Digital Sky Survey paper, PSF paper, sorry. So, but this is just to let you know that you can use this powerful feature for looking into the BCR databases just from the command line, and this is really easy and really fast to use. So now let's go to use some data from Gaia. So we are going to download a catalog. So let's put like here Gaia, the data set number 3. So we are 3. And now, of course, we don't want to download the entire Gaia catalog, but only those that part that correspond to our image. So we can say here --overlap, overlap with, and then our image. Again, download the image and the filter. And now instead of downloading all the catalog, just that part that overlap with our particular image. Now let's specify the columns that we want to download. So for example, the source ID, the right ascension, declination, and then the photometrical magnitude. So the photometrical BP mean magnitude. And then let's put a good name. So Gaia -cat.fix, and that's it. So we have retrieved the data that correspond to our image from Gaia, and you can see here that it consists in a table with 4 columns, which are the ones that we have requested here, and 6 different objects. Okay, if we have a look again with AST table, Gaia catalog and the information, you will see that this is actually the case. This is the raw data. Okay. Now let's move to the next program, which is AST match. Now that we have computed our own catalog with AST make catalog, and we have another external catalog from Gaia, we could make the match in between that 2 different catalogs. And for doing that, we are going to use the next program, which is AST match. Okay, this is a program for making the match of astronomical tables. Let's do it. So give, for example, the first catalog and the extension that we want to use. So the extension number 1, or the clamps, for example, just to put here the name explicitly. Then we are going to use the right ascension and declination for the matching rows. So right ascension, declination. This is what we are going to use for the first catalog, for our catalog. And then do exactly the same for the Gaia catalog. We are going to use the first extension, so HDU2, because this is from the second catalog, number 1. And then we are going to use the right ascension, so see call number 2, again right ascension and declination. And now we have to specify the aperture in which we want to make the match. Okay, so aperture equal to 1 arcseconds. Since we have specifying here the columns in degrees, we have to specify also the aperture in degrees. So divide here by 3600. And then, for example, the output will be Gaia match, and that's it. Sorry, fix. And that's it. We have obtained the output, which is actually the match catalog. So AST fits, Gaia match fits. And you will see that inside of this file, which is the result that we have obtained, we have two different extensions. One corresponds to the object that were present in the, so one corresponds to the columns from the first catalog for the object that are matched, and the other one for the second catalog. If you would like, for example, to obtain one single extension, one single file for the match result, we can specify this with the next option. You could say here -- out columns, so out calls, and then specify which column from each catalog do you want. So, for example, from the first one, you just have to type here A for the first one. I want the right ascension, and also from the first one, I want the declination and the magnitude. Okay, magnitude. And then for the second, which corresponds to the Gaia one, okay, so I put here B, I want the photometrical magnitude. Okay, so BP, mean, magnitude, and now let's put here, and that's it, because we have already specified the output name here. So just press enter, and now if you have a look again at the output, you will see that the output now is only one single extension in which you have the match object from the two different catalogs. Okay, so this is really powerful when matching really large astronomical catalogs, and it is done in parallel and very efficiently and really fast. Okay. Let's now go to the next program, which is for obtaining the statistics of images and astronomical tables. And the name is AST Statistics, as you can see here. Now we are going to obtain, for example, the statistics of the NoiseChisel output. Remember, this image is NoiseChisel. And just press enter, and it is going to compute the basic statistical information of this image. So here you can see that the number of elements, so the number of pixels is this one. It is gonna obtain the minimum, the maximum, the median, the mean, and the standard deviation values. And also it is gonna print on the command line a very nice histogram that is really useful when, for example, you are working on a supercomputing facility and you don't have access to a graphical interface for having, for example, having a look at the histogram or any kind of plot. So you don't have to go to download the data to your local machine and so on. So here we can see that we have some pixels which are very bright. So this is the pixel distribution value. So now we have different options that we can play with. So for example, let's have a look at only those pixels that are below a given value. So less than, for example, 0.005. And then statistics is gonna compute only the statistics for those pixels that are in the range of pixel value that we are specifying. So again, the number of pixels is different, the mean, maximum, the mode, the quantile, and so on, they are different. And as you can see here, the distribution is also different. So this corresponds to the pixels that are fainter, so essentially to the sky background pixels. Okay, so now instead of having a look at all of these measurements, imagine that, for example, you would like to obtain only the mean. So you just have to type here mean, and it is gonna print on the command line really fast the mean. And of course, you can do exactly the same, for example, with the median, and the standard deviation. And for example, imagine that you would like to compute the skewness of this image. So then you will pipe this into occ just to make this computation. Okay, so that's by doing this, we can print the result of computing the skewness. Okay, so the skewness is defined as the mean, so the first column, the mean, minus the second column divided by the standard deviation. So this is a measurement of the skewness of this image, as you can see here. Okay, and now, for example, imagine that you would like to compare this with with the image in which we only have the sky background because the signal were masked as I showed before. Okay, so now you can compare the different skewness of these two different images and see that actually they are different. Of course, again, we have many different operators that you can use here. We have also Sigma Clip. Just to have a look at all of them, you can use the option help or go to the book into the website to check what are the different options and all of the information related with all of them. So another interesting measurements are the ones that correspond to the sigma clipping values. So for example, to obtain the statistics using the sigma clipping values, sigma clipping operator, sorry, so dash sigma clip is gonna compute the sigma clipping values. So let's use, for example, the original image, just to see more iteration with chisel that fits. And it is gonna compute the sigma clipping values for the number, the median, the mean, so the main parameters, right? So you can see that it is computing by default 3 sigma clipping until it reach a given tolerance. Of course, you can change the 3 sigma to be another one, like for example 2 sigma or 5 sigma, whatever you want, and also the tolerance. Okay, so it computes different iteration until it reach the tolerance level, and the final results you can have a look at here. So this is done really fast, as you can see, and it is really powerful. And then again, you can use the AST statistics, for example, with the catalog, not only on images. So if you provide here the catalog that we were measuring before, you can say AST statistics catalog and just press enter. And of course, it is gonna complain because we have different columns that you cannot mix together. So you have to specify a given column. So for example, see magnitude, and it is gonna compute. So this is the line that I have just execute, and it is gonna compute the statistical parameters for that particular column. As you can see here, this is the minimum value, the maximum, and the distribution of values, as you can see here. Okay. So now let's move to high-level features. So now I am going to review, for example, another program, which is AST convert type, and this is designed with the goal of converting different data sets, so for converting data sets into different format files. So for example, let's have a look at the crop image, crop fits. So instead of having a look at the original fits file, with this program, we are going to convert this fits file into a JPG image. So just to specify the output, crop JPG, and it has done the conversion. So right now we can use, for example, AOG to have a look at the crop image. And here you can see that we have this small image in which in the center we have the galaxy. But of course, the appearance of this image is not, it's not so nice. And this is because we have very bright pixels. For example, this one that is in the border of the image. So AST convert by default is trying to represent so the entire range of pixel values in a linear scale. And because of the very central part, so the central part of the very bright object is a pixel value very high, and the sky background are very have pixel value very low, it is almost impossible to have a good image with such huge amount of pixel value. So to solve this, we have the possibility of specifying here a maximum value for the pixel that you want to represent. So flux height, for example, 0.1. And by doing this, of course, we are going to improve a bit the image, as you can see here, but the center is going to be completely saturated. So we have some more information. You can have a look at the outer part of the images, but of course, the result can be improved a lot. So here we have also many other different options. So for example, instead of keeping this image as JPG, you can just save as APS, which is more convenient. For example, when obtaining images for papers and publications, so APS, and it is gonna automatically make the necessary conversion for obtaining in the APS format. So let's have a look at the image that we have just created, APS. Oh, really big. Okay. And here you can see that directly it has been converted to APS. We have different options. For example, we can change the color map, and for example, select the viridis, which is the typical one that Matplotlib used by default, as you can see here. Okay, and we also can compute the PDF, the image in PDF format. Okay, again, if I change to open this image, you will see that this is in, sorry, it didn't change. Crop PDF. Here. So this is the PDF that the AST crop is generating. So now instead of making this kind of fake color image, let's say, since we have 3 different images for the same region of the sky, as you can see here, download, we have been always treating this image, but we have other 2. So this is the redder, and this is the bluer, and this is in the middle, okay? So we can assign each one of these image to one color channel and give all of them to AST convert to generate a color image, okay? And this is actually what we are going to do. So AST convert, we have to give the images from redder to bluer, so download this filter, download the other image in the next filter, and the last one, which is the bluer. Okay. Now let's specify the flux range. So dash flux low equal to 0.0 to not have negative values, and flux high just to keep the brighter regions, 0.001 for example, and then output color.jpg. Okay, and it is saying that I have to specify an HDU for all of the images. So in this case, since I am going to use the extension number 1 for all of them, I can specify a global HDU, so dash G1, and it is gonna make the color image. So AOG, color JPG, and this is the kind of image that we are computing with this image. Of course, it has many different options that you can play with in order to improve the results. But in general, we have the problem that we are showing here the pixel value distribution in a linear range. So to solve this, I am developing a script, which is a collection of, let's say, calls to different Gnuastro programs in order to obtain automatically a good set of parameters to represent color images, to create color images. So this script is actually in this direction. I can download I can download this script. It is not in Gnuastro yet, but we are working to include this script as part as another Gnuastro program as soon as possible. And this is a perfect sample in which you can see that you can use different Gnuastro programs for making the analysis of your astronomical data in the proper way, using the well-defined blocks of programs that I have just reviewed before. So let's give permission to this script that I have just downloaded. And now let's use this instead of the original AST convert. So RGB, and then we are going to use this script on the original images that we were using. So let's modify a bit the parameters. Okay, let's remove this because they are not longer necessary. So again, HDU equal to 1. So basically we are doing exactly the same. We are giving the 3 different images from redder to bluer. Okay, and now we want to specify here that the minimum value is equal to 0 because we don't want negative pixel values, and then specify an output name. So for example, color.jpg. And it is going to make different operations. So arithmetic, as you can see here, arithmetic is being used a lot, and it is able to compute automatically some parameters that you can play with for obtaining a good color image. So let's have a look at the image, JPG, and here you can see that it has computed the necessary transformations for obtaining a better color image. So essentially, this can be improved a lot, as you will see, but basically what it is trying to do is to make the transformation of the pixel distribution using arc-cosine hyperbolic function. So all of the details about this transformation was published some time ago by Robert Lupton, 2004. So you can have a look at that paper to study the details of this algorithm. Here, I am just trying to implement this to have a good tool for obtaining color images. So let's play a bit with the parameter. As you can see here, this is some of the guess that the program has done. And now I can use another one. So for example, --q bright. Sorry, and let's put, for example, 0.4538, for example, and then improve the contrast by a factor of 2. And then let's run this, the same line of code, but just modifying this couple of parameters. And then you will see that now, well, you can see here that the parameters, so the original ones were this one, okay? And now we have changed these ones, okay? So basically, if we have a look here, G color image, you will see that now the image has improved by a lot. Okay, so now we are able to see the inner part of the galaxies and the stars together with the outer part and the sky background in a much better way. So this is just playing a bit with the parameters, but in principle, you will be able to play and improve a lot the parameters that it is possible to use with this kind of scripts. So now I have some minutes in which I can keep going to show a couple of things about how to generate some profiles and making the convolution of astronomical images. So let's do this once we have reviewed this script. For example, we are going to use the AST-mkey-prof to obtain astronomical functions, some profiles. Okay, so for example, we want to obtain a kernel, which is a Moffat, a function equal to a Moffat. So kernel equal to Moffat, and then the parameters of the Moffat. So an alpha, a beta, so 2.8, for example, and then the truncation radius 5, and then specify that you want to have an oversample of 1, so just 1 pixel, oversample equal to 1, and then the output that we are going to call Mohammad. Okay, and really fast, it has computed this image. So let's have a look at the image, Mohammad. And you can see here that it is actually the shape of a Mohammad. Okay. In the same way, we can specify that we want to obtain, for example, a Gaussian function. So for doing this, the Mohammad, the Gaussian only have 2 parameters. So remove the beta. And then let's call this, well, you have to specify here Gaussian, and then let's call it in a different way. So Gaussian, and now it's gonna create a Gaussian function in the same way than before. Okay. Now we can use this Gaussian or this Mohammad function to make the convolution of the original image with this kernel. So, and to do that, I am going to explain another program, which is AST convolve. AST convolve. Okay. So now we have to specify the original image. So download this filter, and then the kernel that we are using. So kernel, for example, the Gaussian, and the space in which the domain in which we want to make the convolution. So in this case, we are going to make the convolution in the spatial domain. So dash domain, and then spatial, and then the output name. So convolve.fix. So again, we are using the input image and the kernel Gaussian that we have just created with the previous call to AST make profile, make the convolution in the spatial domain, and then let's do the convolution. Let's have a look. So we can open the original image just to compare, and the convolve with DS9 at the same time, just to see how we can make the filter, the smoothing of the image. Okay, just to have a look here, let's match everything just to compare the 2 different images. So as you can see here, the convolve one has increased the signal to noise, but of course the resolution has been decreased. Well, not the resolution of the pixel, because the pixel size is essentially the same, but actually we have a smooth image, right? So make the convolution with the Gaussian kernel. So this is something that you can do directly from the command line. And then just to finish, I would like to show a very nice example on how we can use different other tools of Gnuastro for making a catalog, a synthetic catalog, and then make a kind of simulation of a galaxy with a string. So here we are going to make a catalog. Just let me copy directly this line. Okay, so this is a bit strange at the very beginning. You can ask to Mohammad at the Discord channel, but basically we are putting here some parameters that will be used for AST make profile for building some objects. Okay, so in this case, for this one, we are encoding here the necessary parameters for creating the PSF. Okay, so this is the PSF, and now we are going to put a galaxy, which is a CERSIC profile with an index equal to 1, as you can see here. Okay, at this position, and many other parameters, so the position angle, and so on. So let's keep this in the same file, and then let's put a string, which is also a ring of pixels that we are simulating. So now that we have created this file, let's have a look. So cat.txt, this is basically the parameters that we are using for making the simulation. No? Now let's use AST make profile to make the synthetic image. So we can specify here that we have a particular size. So let's give the catalog.txt merge size, for example, equal to 600 and 600. The mode is in image because we are not giving world coordinate on the sky. We want to over sample this 5 times, 0 point of equal to 30, for example, and then which is for the stream equal to 20, and then output, for example, no noise because this is not having noise yet, and no convolution. No convolve dot fits, and it is gonna create this synthetic image. Okay, so let's have a look at this image really fast, and you will see the kind of image that we have created. Okay, so at the center we have created the galaxy, and we have a ring here that corresponds to the stream. And this has been computed only using the Gnuastro AST make profile with the parameters that we have specified in this file. And now the thing that we are going to do is, well, let's move this file that it is the PSF, the kernel. Okay, let's move and call it like kernel. So this could be a bit strange at the very beginning, but you have the instruction that I am following into the website, and in any case you can ask in the Discord channel. So there is no problem. So now we are going to convolve the image that we have just created with the kernel. So let me just copy and paste the line that I am putting here. So again, AST convolve, the original image and the kernel that we have just created. Just execute this, and then we are going to warp, which is another program that I don't have time to explain right here, but you have the information. So we are warping this. Okay, we are transforming the pixel scale. So let's do this step. So let's have a look at this image. No noise, oversample. Okay.
Raul, just a note, you have 10 minutes left over.
10 minutes?
Yeah.
Okay, perfect. Perfect, thank you. So just to have a feeling of what I am doing, we have simulated some, let's say, some real condition of the observation. So we have resampled the image and so on, and now we are going to add the noise. So in AST arithmetic, we have the possibility of doing that with the operator make noise. So with arithmetic, I am giving as an input the image that I have just created. I am going to transform the magnitude to counts and then make Poissonian noise. And then the output, as you can see here, will be somehow a realistic observation of this galaxy. So galaxy. And this is the kind of simulation that you can do. Of course, this is very simple, but here you can see, oh, we have simulated a galaxy with a stream around this galaxy. And now we can start playing, for example, with NoiseChisel for making the detection or comparing our techniques with another different catalogs. Okay, more or less, this is all that I wanted to show. Just to let you know that, of course, we have something that are not programs yet. So IST, we have reviewed almost all of the different programs, but then we have some scripts that, as I said before, they are higher level scripts. They are actual scripts, as you can see here. So let's have a look. For example, if you type here which AST script radial profile. This is a script for making the radial profile of astronomical images, given a particular position on the sky. So if we have a look actually at the script, so it installed, as you can see here, in this direction, in the conda environment, and this is actually a shell script, and you can see that we have developed this using many different Gnuastro programs. So here you will see that, for example, for computing the center, we are using AST table with the WCS parameters that we have previously used. For example, here for obtaining some parameters, we are using AST feeds, then AST statistics for making the calculation of some parameters, and so on. So this is actually an example on how you can use the different Gnuastro programs to put all of them together into one single script for making the analysis that you want to obtain. Okay, and now just to finish, let me say to you, okay, this is the notes that I have been following. You have all of them into the Discord channel into the webpage. And just to finish, let me have a look at the Gnuastro book, just to say to you that even though we have used in this tutorial the conda installation, you will see that Gnuastro has a very few dependencies. So let me make this window a bit bigger. So here you have all of the different formats in which you can have a look at the documentation in HTML directly on the website. So you have here the index, table of contents, but of course you also have the PDF, the already compiled PDF in which you can have a look here. So this is the PDF. As you can see here, we have different sections. We have a very wonderful section in which you can start playing with nice tutorial from the very beginning. Okay, and then about the installation, you will see that dependency that we have to install Gnuastro from scratch are just 3. The first one is the GNU Scientific Library, CFIT-SIO, and then the the WCS library that you can see here. All of them are explained here in detail, and actually you can see here that you have the different steps that you need to run on the command line for installing all of them, and of course also Gnuastro itself from scratch. So since it has a very few dependencies, it is possible that many different Linux distributions have already compiled Gnuastro. You can see here the list of all of the different GNU Linux distribution that has already compiled Gnuastro. So for example, compared with AstroPy, and because AstroPy have many different dependencies, some of the Linux distribution are not able to compile them as easy as Gnuastro, right? Pi, you will see that the list is much smaller. And actually some of the distribution has already the latest version of Gnuastro, as you can see here. And then just let me finish showing that, of course, if you find the Gnuastro is useful for your particular research, you can use the feature cite. So for example, imagine that you are using NoiseChisel, AST NoiseChisel. You have the option --cite to have a look at which paper, which documents do you have to cite in order to acknowledge, for example, this particular program, which is Gnuastro. So I will finish here. I think we have time for a couple of questions. So thank you very much to all of you for attending to this tutorial. I hope you have enjoyed. Thank you very much.
Raul and Mohammad, thank you so much. This great talk. I think we can give them a round of applause here.
Thank you.
I don't know if the participants here in attendance have been following Discord, but that's been very active. Is there any questions from the group here in person that that we can ask. We can use the microphone here if you have any questions. You can come up, yeah, sure.
So I think somebody is talking, but I cannot hear. Some of you are hearing something?
No, we don't hear anything.
So Mohammad, please feel free to answer the question if you think.
No, I see in the video that
okay.
someone is talking, but I don't hear anything.
Okay. Okay.
And now?
Oh, yes.
Okay, cool. Thanks. So I was particularly interested in the feature that creates the RGB images. Is it possible with Gnuastro to then overlay contours of another image on top of that RGB image and then export it as a PDF or PNG or whatever? You know how you can do that with Apple Pie with Fitzfigure? Is that something that's possible with Gnuastro?
So you mean, for example, make some annotation? So like putting arrows or some text within the image?
Yeah, some annotations or whatever it is you want to do, and then export it.
Well, actually, with the programs that we have, I think it is not possible. Correct me if I am wrong, Mohammad, but it can be.
Yes. Go on.
No, go on.
So the thing is that, Raul, I'll send you this link of this paper in the chat that you can show. So this is a trick, actually. It's not that we have right now. Do you have the chat in the Zoom?
Yes.
That what I've done was to manually play with the color channels to add the contours that I wanted, and you see it works nicely. But yes, so Raul, if you can show it. No, it's in the chat of Zoom. Sorry, I should have put it in.
In the chat of Zoom. Let me. How can I open the chat of Zoom?
So maybe I can put it on Discord.
Yes, maybe. Yes, I know this is in the Gnuastro book.
So I put it on Gnuastro. Yes. No. This is in one of the papers that announced version 10. So if you go to figure 2, we have a case. Go down. The second figure, and no, one more, the third one. Sorry, bad memory. Here you go. So you see, what I've done was that in each color channel, like in this scenario, I wanted to show the surface brightness, essentially levels around the detection of this galaxy. So you see, I just effectively put the Sextractor edges on the red channel, the NoiseChisel edges on the blue channel, and then like this NoiseChisel optimized on the green channel, and it worked really nicely to show these features in a per pixel base. To show vector-based contours, if you want a vector, so this goes into the pixels of the color image. But to show vectors, what I do is to for example, I take the EPS output and then I just draw contours with PGF plots in LaTeX, for example, right now. But that is really a feature we plan to add, and in fact, I think we have a task for it. Thank you for mentioning it. With your question, its priority will go up. Thank you.
Oh yeah, it would be a great feature to have. Thanks.
Yes.
Thank you.
Is there any other questions from the floor? Okay. Raul, Mohammad, thank you so much. I think the discussion may continue inside the channel on Discord, and so you guys feel free to add any questions there that you may still come up with in the next few minutes.
Thank you so much for organizing it.